In our study of the death of stars, the final and most extreme type of object that can be produced by giant stars is an object called a black hole. And no, this is not a portal into another dimension, but it is interesting nevertheless. So let's look at some of the characteristics of these enigmatic objects. So what is a black hole and what produces it? The term first was coined by John Wheeler in 1967, but the origin of the black hole theory came from John Mitchell in 1783, proposing the idea of a star so massive that the escape velocity exceeded the escape velocity of light, and therefore it would be known as a dark star. If such an unimaginably dense star would exist, so that light itself, moving at 300 million meters per second, could not escape the surface, then, well, the star would be dark and invisible. It would be a black hole. Well, do black holes really exist? Good question. Just as the whole concept of neutron stars was unpalatable to so many scientists because the conditions associated with a neutron star just seem out of proportion with all other known aspects of reality. Black holes take that another step. So a lot of resistance to thinking that this is actually a correct description of reality. However, just as white dwarfs, because of the Chandrasekhar limit, cannot exist larger than 1.4 solar masses, neutron stars likewise have a similar type of mass limit. And that mass limit is that it must be less than 3 solar masses. So a neutron star cannot exceed 3 solar masses. If it's higher, neutron degeneracy pressure cannot hold off the onslaught of gravity. So we saw that high mass stars, which are stars between 8 and 25 solar masses, and their lives as neutron stars. But when you get beyond 25 solar masses as the initial mass of the star, neutron star remnant is then greater than 3 solar masses, and neutron degeneracy pressure loses in the war against gravity. And so there is now no known force in nature that can stave off the onslaught of the crush of gravity, and the neutron star crushes down into an object known as a black hole. To provide a little background so that we can embrace some of the ideas we're going to encounter with black holes, we need to discuss a little bit about the ideas of relativity. And first, special relativity. When we talk about relativity, we're, yes, talking about this character Einstein, who came up with some really amazing ideas that have proven themselves to be very true in terms of matching the reality that we can measure. So special relativity, his theory that was produced in 1905. Most of you are familiar with E is equal to mc squared, the relationship between energy and mass through the velocity of light squared. So that's an amazing aspect of his special theory. Well, the special theory has 2 basic postulates, and they are that your measurements of physical reality are the same at any constant velocity. Another way to say that would be that the laws of nature are invariant in any inertial reference frame. So all your measurements in your reference frame when you're moving at any speed through space are the same as anybody else's. That may not seem too strange. However, it does establish things like if you throw a ball up in the air, it'll come down to your hand. Now, if you're moving in a supersonic spacecraft doing the same thing near the surface of the Earth, and you throw a ball up into the air inside that plane when you're moving at, say, Mach 2, it's going to come down to your hand at the same time as well. Also, the speed of light is always the same for all observers. So if you happen to be moving on a train that's moving at half the speed of light, you take a flashlight and shine it, you will see the flashlight beam moving away from you at the speed of light. An outside observer seeing your motion at a half a speed of light plus the motion of the flashlight beam, which is moving at the speed of light according to you, the person observing you doing that will see the speed of the flashlight beam moving not at 1.5 times the speed of light, but at the speed of light. And it's the same for all possible observers in any given situation. So that's really pretty strange. Time is dilated and length is contracted for a fast-moving object. So here we have a fast-moving train. And as you observe that fast-moving train, you'll notice its length is contracted, not its width, no spatial dimension other than the one in which the motion is observed. But time is dilated too. So here's kind of a couple clocks putting that idea together. Stationary clock, moving clock. The moving clock is length contracted. And notice that the time is less. Not as much time has transpired during that motion on the moving clock. So time is like an elastic band, and that is highly counterintuitive. Mass also increases at high speeds and approaches infinity as you approach the speed of light, which is one reason why you can never get any object that has mass, any rest mass, to move at the speed of light, because it would take infinite force to achieve the speed of light because the mass is going to infinity. So space and time are really not distinct entities. We've seen that just now, that as you move through space, time does not stay constant. So there's a relationship between space and time. There's an interconnectedness between them. So we can think of them better as a quantity, a physical entity known as space-time. One way I like to think about this is that everything moves through space-time at the speed of light. Therefore, if you're sitting there in your chair right now, you're not moving through space, and all the motion through space-time is concentrated on causing time to take place. You're moving through time in this space-time. None of this motion is through space for you right now. It's all through time. If you're moving just about the speed of light, then all your motion through space-time is used up, so to speak, in moving through space. And time, at least for an outside observer, would be seen to essentially come to a stop. So I know that's very mysterious. It is for anybody, including Einstein. Nevertheless, it matches reality. And it is something that we need to consider and ponder, that what we perceive in terms of space and time is not necessarily consistent with reality. In addition to special relativity, Einstein came up with his general theory of relativity, which was actually a lot more impactful into our understanding of the nature of space and time than his theory of special relativity. It included the idea of accelerations in addition to just constant motion and inertial reference frames. And it made it a lot more complicated. And here in this little image, he's shown writing on the board something called the tensor equations for space and time. Anyway, it's very complicated, but very well tested. And his initial insights were that gravity and acceleration are identical, so that you can't distinguish between a gravitational field and motional acceleration. Well, a consequence of this whole thing that we're not going to get a really deep understanding of right now, or later for that matter, is that matter warps space-time. And so here we see a sequence of graphics here representing space-time as flat two-dimensional surface. And so you put masses there, and you'll notice that the matter warps or curves space-time. And that is actually what he helped us understand. And in the process of this curvature of space-time, the matter interacts as well. So when you put the masses closer, the curvature bleeds into each other. And so it can be said that the curved space-time informs matter how to move. And in fact, it informs photons as well. So this curvature of space affects how photons move through this space-time fabric. And this is just an analogy. It's a little overly simplistic. Space is not in a two-dimensional sheet, but it enables us to visualize a little bit of this. So that's helpful. Einstein became famous, and his face was in the headlines all over the world after he predicted this and said, you know, a mass will curve space-time. And so if you look at the position of the star, as the starlight grazes the edge of the sun, it'll warp or bend the starlight by 1.75 arc seconds. Well, in 1919, Sir Arthur Eddington, during a solar eclipse, was able to observe the position of a star that was grazing the edge of the sun. During a solar eclipse, it was dark enough so you could actually see it. The position of the star was over here, because here's the actual star. The sun bends the light, so as you project backward, you're observing the star in a different place. So Eddington was actually able to confirm the 1.75 arc seconds that Einstein had predicted. It was a bold prediction, because photons don't have any mass, so people didn't really think that a gravitational field would affect its path. But indeed it did, because space itself is actually curved. So that's really pretty amazing. Moreover, time is dilated not just by fast velocities, but by gravitational fields or the bending of space as well. So that time, as recorded from Earth, a clock on Earth, is going to run a little slower than time or a clock measuring the sequence of events in a smaller gravitational field. With very accurate cesium clocks, this can even be and has been measured on Earth. So if you put a clock deep in some basement, or just say on the surface, and go to a top of a tall building or up a mountain with a synchronized clock, the rate at which time progresses at the higher elevations is greater. This is also established and understood to the point where the GPS satellites that we're all familiar with, or at least the resulting technology, the GPS units themselves, would not function correctly if this was not taken into account. The speeding up of time from the satellites being way up there, high above the surface of the Earth in a smaller gravitational field, and the slowing of time as a result of their fast velocity. Both of these effects are real, and if they weren't taken into account, the GPS information that we utilize and are very fond of, I know I am, would send you off into locations that are incorrect. You think you're in Chicago, and it's actually telling you you're in Toledo, Ohio, or something like that. Gravitational redshift and other things are also predicted by Einstein's equations, and they're not only predicted but measured to be extremely accurate. So his theory has been validated to many decimal places, and actually general relativity is a more well-established theory than Newton's laws of motions are. At least they're measured to more decimal places more accurately than Newton's laws. In fact, this theory even tells us the shape and the development, the evolution of the universe as a whole. It's explained. For instance, the expansion of the universe is predicted by the general theory of relativity, and subsequently it has been measured to be expanding. So this is an amazing insight into the reality of the universe we live in, and it will help us not to be so surprised by the reality of the black holes that we're going to discuss.